so that so our aim is FET biasing. So, so the first condition is the Q point should be independent of the device parameter variations and ambient temperature. So this should be achieved by proper VGS or minimum VGS. Voltage. And the second one is proper drain current. So these two conditions you have to maintain so that the FET becomes properly biased, right? So for this, I think so the first condition is the proper functioning of JFET or any FET amplifier. It is necessary to maintain the Q point is at the center of the pitch of it. So this is the curve, right? So from here to here, this is the pinch of region. So when you draw a load line, the point should be at the center. So this should be in the pinch of region, center of the pinch of region, right? So that to maintain this Q point at the center of this pinch of region, what is the necessary condition here? We are using a proper VGS, a voltage is maintained, and a proper ID current, drain current is maintained. So to get this, we have three types of biasing we are using. One is the types of biasing. I think this is also, I have gone through last class and previously in the BJT also we have studied about this types of biasing. Same biasings we also are using. One is the fixed bias. And the second one is the voltage divider. Voltage divider. And the third one is the drain to gate resistance. So this is especially used for EMAS. We will not use this for general FET, JFET. These two combinations are used for JFET and DMOS. Right? So fixed bias, voltage divider bias, and drain to gate resistance. So for all these bias, when you add similar what we discussed in the BJT, the emitter resistance is added, right? In BJT, we add emitter resistance RE, right? When you add emitter resistance, that becomes a self bias. If you add this RE to the transistor, automatically, whether it is in a fixed bias or it is in a voltage divider bias, that bias becomes a self bias. So same here. Here also fixed bias. If you add resistance of FET or FET, you have to add RS, source resistance. If you add this source resistance to any one of these bias, this becomes a self bias. So for example, if you take a fixed bias, so for this fixed bias, if you add source resistance, then we can call this as a self bias also, right? If you take a voltage divider bias, if you add emitter resistance RS, then it is also called as a self bias. So when you add RS resistance, automatically the resultant bias you can just call it as a self bias. So it is self-controlled. How this is controlled, self-controlled by that we will see here. So first of all, we take the fixed bias. So for fixed bias, you have to go through. FET is the FET symbol you have to draw. Right. To this FET, just I am adding the gate resistance, RG. RG is the gate resistance. And here we have to apply minus VGG, gate voltage. And this is the common source configuration. So as we discussed earlier, uh, just like in a BJT, the common emitter is a commonly used configuration, right? Commonly used configuration. The same here, common source, common source configuration. Configuration is widely used, same as a similar as a CE in BJT. So common source is a common source amplifier or common source configuration is widely used here, right? So this to this fixed bias, this is the output V0 and this is the input VA. So this is a simple amplifier circuit with a fixed bias. So for fixed bias, RD is connected to drain resistance, right? This is the drain terminal, this is the source terminal, and this is the gate terminal, right? So from gate terminal and a high input impedance, a high input resistance of RG, which is greater than 1 mega ohm. 1 mega ohm is connected. So generally, what in the previous discussion, because of gate junction is reverse biased. Gate junction is the input junction, right? Here in the JFET. Gate junction is reverse biased. The input resistance, input, input, the input resistance of the input resistance RI is very high. Is very high. This is already we discussed. Why it is input resistance is high? Because of gate junction is reverse bias, a heavy reverse resistance is acting there. So that reverse resistance is we are considering here as a gate resistance or input resistance, right? So that's why the gate is already IG. The gate current flowing here is IG, right? So we have to replace this circuit into the DC mode. So what is the condition I told for DC mode? The AC components which are present here we have to remove, is it not? So that can be replaced by in a DC mode. And the DC biasing, so we have to keep it as it is. Sometimes there is no DC bias here, that also we can remove. That also not present. So at that time, just IG becomes 0 or VGS is equal to the 0. So this becomes VDD. And here, gate terminal, there exists a gate voltage of VGS. Similar, just you have seen as a మనకు ఇంతకుముందు ఎలాగైతే బీజేటీలో చూసామో అదేవిధంగా గేట్ సోర్స్ అక్కడ మనకు బేస్ టు ఎమిటర్ వోల్టేజ్ VVG అని చదువుతున్నాం. Similarly, here also we are calling as the gate to source voltage called VGS, right? So simple, you can draw the KVL on input side and the KVL on output side. And here is the voltage of VGS, VDS. Right? So from the input KVL, what we can draw? Minus VGG equal to VGS. Because there is a heavy resistance placed here, the current passing through this IG becomes 0. It becomes 0. So nothing but the what is the gate voltage? There is no question of any drop here. We're just neglecting because of heavy resistance here. So just VGS is same equal to the applied voltage VGG. Suppose if this voltage is not given, sometimes this voltage may be not given, right? This voltage may be not given. So at that time, we have to replace the circuit as like this. This is equal to RG, right? So at the time, VGS equal to 0 because there is no VGG here. VGG becomes 0 here. So at that time, VGS equals 0. So like this also we can show. Is it not? Is it clear? So this is about the fixed bias. So in the fixed bias, there is resistance, there is existing in RD resistance and RG, a drain resistance RD and a gate resistance of RG. The RG should be, the value is very higher value, more than 1 megawatt. Or sometimes it may take a 500, more than 500 kilo ohms also. So for this circuit, just you replace the equivalent circuit here, right? After getting this equivalent circuit, then we have to observe the here when the drain current is increased. For example, how this is balanced, right? How this is controlled. You can just observe here. When the drain current ID, right, increases, the voltage drop across RS. RS is not here now. So we'll go to the next one. So coming to the another circuit, same in a fixed bias, fixed with self, fixed with RS, called as a self bias. Fixed bias with RS bias. It is also called as a self bias. So same circuit I am replaced here, a fixed bias circuit. The fixed bias consisting of an RS circuit, right? An input resistance RG, and here an RS resistance is placed, right? Similarly, an RG. Right? So this is the circuit with RS. So now I am placing RS here. So now VGS voltage now we have representing here is VGS is up to here only. This point, this is source. This is the gate. This is the drain. Right? This is the circuit. So what I did modification here, just I am adding the RS. Source resistance is added. So that I can call this fixed bias, can also call as a source self bias. Is it not? So to go for analysis for this one, similarly, here the voltage across here, this I am taking it as VDS, right? And from here to here, the voltage drop across this I am taking as VS. Please copy all these things in the notes. Please copy all these things in the notes simultaneously. Because I am recording this also, you can later on also you can go through the recording video and you can copy the things. Okay. So I am taking this from drain to source. There existing a voltage called as VDS. The existing voltage called as VDS. Right? In the earlier the VDS is from here to ground. Source resistance not there. At the time the source resistance is not existing there. Now we are introduced the source resistance, so that I am calling as a self bias. So in the self bias also, there is VDS is now from here to source only, drain to source only, this part. So the drop across the source resistance I am taking as VS, right? So therefore, when I draw the KVL on output side, what happened? KVL on output circuit. ఏమొస్తుంది కేవలం అవుట్పుట్ సర్క్యూట్ చేస్తే VDD equal to the current flowing through this is ID. The drain current is always ID here, right? And the same drain current is also flowing here also. Don't be confused. IS is equal to ID. IS is equal to ID, right? IS is equal to ID. Just like what we study, because the gate current is zero. Gate current zero కాబట్టి IS is equal to ID. మనకి అక్కడ ఎంటర్ BD ఎలా వస్తుంది? I is equal to IB plus IC, right? IB అనేది intermediate point, that is a negligible value. So ID we are making zero. అప్పుడు I is equal to IC అవుతుంది. I is equal to IC. Similarly, ఇక్కడ gate is already reverse bias కాబట్టి almost the gate current is equal to zero. So that the same drain current is flowing in the source also. The same drain current is also flowing in the source also. So that is called as ID. So that's why I am calling as IS is equal to ID. So I'm writing the KVL on the output side. On the output side, VDD is equal to ID into RD, right? ID into RD plus VDS plus ID into RS. Is it not? ID into RS. So I'm taking ID as common here. This becomes RD plus RS plus VDS, right? So what I have to extract here? I have to extract the VDS now. So VDS is equal to VDD minus ID into RD plus RS. So finally we are extracting the VDS now, right? So VDS, drain to source voltage, is equal to this one. Similarly, when I go to the KVL on input circuit, KVL on the input circuit, VGS is equal to VGG minus VGG, right? Minus VGG minus ID into RS, because reverse voltage now, reverse process, right? So VGG మనకు లేదు కదా ఇక్కడ, VGG we are making it zero, కాబట్టి this become 0. So this is equal to minus ID into RS, is equal to minus ID into RS. Is it not? VGS is equal to what is the applied voltage minus this voltage, drop across this. అంతే కదా, కేవల్ రాస్ ఒకవేళ కేవల్ రాస్ ఎలా వస్తుంది? మైనస్ VGG is equal to VDS plus ID into RS. This implies VGS. Last one. Sorry, VGS. So VGG minus VGG is equal to VGS plus IDRS. So VGG లేదు కాబట్టి this is become 0. So VGS is equal to ID minus ID into RS. So these are the two equations you have to remember, right? VGS రాస్తున్నాము and ID VDS రాస్తున్నాము. So when the drain current here is slightly increased, right, the voltage drop across RS increases. ఎందుకు మనం చదువుకున్నాం ఆల్రెడీ, the channel లో కరెంట్ ఫ్లో ఎక్కువ టెంపరేచర్ రైజ్ అవుతుంది. టెంపరేచర్ రైజ్ అయినప్పుడు ఆ కరెంట్ ఫ్లో ఏదైతే ఉందో ఈ రెసిస్టెన్స్ లో, సోర్స్ రెసిస్టెన్స్ లో వోల్టేజ్ డ్రాప్ క్రియేట్ చేస్తుంది, రైట్? సో అక్రాస్ ద RS the voltage drop is increased, right? The increased voltage drop increases the reverse gate voltage. అంతే కదా, VGS is equal to ఏం చెప్పాలి ఇక్కడ మనం? VGS is equal to minus ID into RS. So ID into RS is a voltage drop across the RS. So RS no voltage drop పెరిగిందని చెప్తున్నాను because of increase in ID. As the ID current is increases, the voltage drop is increased. So it's internally VGS is increasing అని చెప్తున్నాను. So automatically internally the reverse gate to source voltage is increased. As the reverse gate to source voltage increases, the barrier width also increases, because gate junction is a reverse bias. So which decreases the effective width of the channel. Is it not? మన ఛానల్ చెప్పాము ఇలా చేసినప్పుడు ఛానల్ విత్ ఇలా వస్తుందని చెప్పాను కదా. సో ఈ ఛానల్ దిస్ ఇస్ ద ఎఫెక్టివ్ విత్ ఛానల్ విత్ ఈ పార్ట్ ఉన్నాయి ఇదంతా ఎఫెక్టివ్ ఛానల్ విత్. దిస్ ఎఫెక్టివ్ ఛానల్ విత్ ఈజ్ డిక్రీజెస్ బికాస్ గేట్ జంక్షన్ వోల్టేజ్ ఇక్కడ పెరిగిపోయింది. గేట్ జంక్షన్ వోల్టేజ్ పెరిగిపోయింది. ఎందుకు ఎలా పెరిగింది? బికాస్ ఆఫ్ డ్రాప్ ఇన్ ఆర్ఎస్ ఇస్ ఇంక్రీజ్. డ్రాప్ ఇన్ ఆర్ఎస్ ఇంక్రీజ్ అయింది కాబట్టి VGS is equal to minus ID into RS అంటే డ్రాప్ అక్రాస్ RS అది పెరిగింది. సో యాజ్ VGS increases the effective channel width is decreases, right? Decrease isn't the meaning in again the flow of charge carriers through this channel is decreases. So it control just automatically. So when the flow of charge carriers is controlled means again the ID current flowing here is the ID current flowing here is decreases. So ID automatic decrease అవుతుంది. ID decrease అంటే మళ్ళీ ఆటోమేటిక్ ఏమవుతుంది? ద జంక్షన్ గేట్ జంక్షన్ మీద అప్లై అంటే ఈ RS మీద వోల్టేజ్ డ్రాప్ ఏదైతే ఉందో ఆ వోల్టేజ్ డ్రాప్ ఏమవుతుంది? ఈ గేట్ జంక్షన్ వోల్టేజ్ ని తగ్గిస్తుంది. సో ఆటోమేటిక్ ఏమవుతుంది? మళ్ళీ ఎఫెక్టివ్ ఛానల్ విడ్త్ మళ్ళీ పెరుగుతుంది. అప్పుడు మళ్ళీ కరెంట్ ఎక్కువ ఫ్లో అవుతుంది. అంటే ఏమవుతుంది? ఈ రెసిస్టెన్స్ ద సోర్స్ రెసిస్టెన్స్ విచ్ ఆర్ కీపింగ్ హియర్ దిస్ ఈజ్ ఆటోమేటికల్లీ కంట్రోలింగ్ ద ఫ్లో ఆఫ్ కంట్రోల్ ఆఫ్ ఎ డ్రైన్ కరెంట్. ఈ డ్రైన్ కరెంట్ ఆటోమేటిక్ కంట్రోల్ చేస్తుంది. That's why this RS we are calling as a self bias. RS is called as self bias. The bias applied on VGS is through this RS, right? Adhamothunda? Are you clear my point? Respond anyone.
Yes, sir.
So like this, as the drop in RS is increases, the drain current is controlled, right? So that the totally you can call it as a RS is called as a self bias resistance, right? So this is the way in a self bias with fixed bias the FET is operated. So this bias may also apply for a DMOS also, because DMOS is operating for gate reverse voltage, right? VGS DMOS మనం గేట్ సోర్స్ వోల్టేజ్ నెగిటివ్ ఇస్తాం కాబట్టి దిస్ కెన్ బి అప్లికబుల్ ఫర్ నెగిటివ్ వోల్టేజ్ ఆల్సో, రైట్? కాబట్టి బయాస్ మనం యూజ్ చేస్తాం, రైట్? కమింగ్ టు ద నెక్స్ట్ వన్, దిస్ ఇస్ అబౌట్ ద so coming to the voltage divider bias. Voltage divider bias. This is also called with RS. With RS means you can call this as a self bias. So the circuit is same, quite simple. What we studied in PJT. So a drain resistance is used here, and at the same time a source resistance is used here, RS, and this is called as RD. And the applied voltage is VDD, drain to drain voltage VDD, and this is the gate terminal. This is the drain terminal. This is the source terminal, right? And voltage of just like what how we used in BJT biasing, similar method I am using. It's gone, and this is the circuit. This is a circuit, this is R1 and this is R2. So this is the bias, so voltage divider bias. So in this bias, so we are just connecting the R1 and R2 resistors. This is not in series, this is a junction here, a node here. So therefore R1 and R2 are in parallel. So the effective resistance I am writing as this equal DC equivalent circuit. I'm writing as DC equivalent. So in the DC equivalent circuit, what I am doing, just I am replace the same circuit, but without any components of AC components. So the effective resistance I'm taking as RG. MHU RG because these two are in parallel connection, right? These two are in parallel connection. So R1 R2 by R1 plus R2. And the voltage drop across R2 is called as VGG. The voltage drop across R2 I am taking as VGG. So VGG equal to MHU. VGG equal to R2 into VDD by R1 plus R2. Same, similar manner. మనం అక్కడ బీజేటీలో ఏం రాసాము విసిసి రాసాము కదా కాబట్టి ఇక్కడ విసిసి వస్తుంది ఇక్కడ విడిడి అంటే డ్రైన్ వోల్టేజ్ కాబట్టి విడిడి అని రాసాం అంటే విజిజి ఈక్వల్ టు R2 ఇంటూ విడిడి బై R1 ప్లస్ R2. సో దాని ఈక్వలెంట్ సర్క్యూట్ ఎలా చూపిస్తాను నేను దీన్ని సర్క్యూట్ని the equivalent circuit can be shown like this. RG the current of ID is flowing here and the current of IG is flowing here. IG almost 0, you can say that, and this is called VGG. Okay. So this is this voltage is called VS, drain to source. Okay. Right. So drain from here to here, the voltage across this is VDS, and this RD current flowing is ID, and same current is flowing here also ID, right? So when I write the VGS input KVL last time also input KVL implies VGG equal to, earlier we said that VGG equal to negative, right? Here it is not showing, but it is a negative voltage. VGG equal to, right, VDD VGS voltage. This voltage is called as VGS. Right? Because VGS. So VGG is equal to VGS plus ID into RS. Is it right? Because the same current flowing here. If ID is number, the same current is also flowing here. Here also ID. Probably ID into RS will be the drop, voltage drop across this. That is called as VS approach. You can call this a VS approach. VS approach. We want the videos. So VS voltage plus VGS voltage is equal to VGG. Other answer. VGS is equal to VGS plus ID into RS. So VGS is equal to MHU. This implies VGS is equal to VGG minus ID into RS. So this VGS is equal to voltage here, VGG into minus IDRS. This always should be a negative voltage. And VGG voltage drop అంటే ID into RS drop ఎక్కువగా ఉండాలి. Such that the resistance RS should be selected. This voltage should be negative voltage రావాలి. So that the gate junction becomes reverse bias. అది గుర్తుపెట్టుకోండి. The VGG voltage which you drop across this R2 should be lesser than the drop across RS ఉండాలి. అలా వచ్చే విధంగా we have to take this combination of resistance values. ఎందుకు? Because the gate junction always reverse bias ఇక్కడ. కాబట్టి the voltage which you are taken here, the drop across IDRS, the drop across RS, IDRS, that is equal to more than this VGG ఉండాలి. Right? ఇక్కడ మనం always this should be a negative value రావాలి. అప్పుడే the gate junction reverse bias లో ఉంటుంది. అది కండిషన్. వచ్చే విధంగా we have to consider, we have to take it. Right? And coming to the output cable, output cable. So in the output cable, mostly output law implies that just it is VDD equal to IDRD plus VDS plus ID into RS. Is it not? Same, if you take the ID as common here, this implies ID is, if you take ID as common, this implies RD plus RS, right, plus VDS. Is it not? ID has to take it as common, RD plus RS plus VDS. So this is the analysis part we have to consider, right? For a voltage divider bias. For a voltage divider bias. So coming to another method, another process, another technique called as a drain to gate, right? Drain to gate bias. This is applicable only for EMOS. Because gate junction, gate voltage here is a positive voltage. కాబట్టి gate voltage DMOS ki JFET ki use చేయడానికి వీలు కాదు, right? So the circuit is simple, quite simple here. The VGG of positive voltage is given here, the VGG, right? Which is given to the EMOS. This is for EMOS. EMOS can be replaced by a total lens. And the feedback resistance here, R. The drain, gate, and the source. So this is a circuit. Same thing, the voltage across this one, VGS. VGS is equal to what is the drop across the RG. The drop across the RG. The drop that is called applied on VGS. So VGS is equal to, what is the drop across this one? Here I am using a gate resistance and the feedback resistance R. So eక్కడ నాకు drop కావాలి across this కదా. ఇక్కడ voltage ఎంత? This voltage I am taking as VD, or I can call it as a VDS. Okay, this is called as VDS. Is it not? From here to at this point, the voltage drop is VDS. Is it not? The current passing through this is ID. ID is common. ID, same ID is also flowing here also. right? But instead of connecting this RF, earlier the voltage divider bias we are connecting this resistance here, is it not? Now, not here. Now in the feedback method, we are connecting the resistance at the drain terminal. At the drain terminal. So therefore, ఇక్కడ ఎంత voltage ఉందో, what is the voltage measured at the drain? This voltage మనం ఇక్కడ డ్రాప్ చేసుకోవాలి. ఇక్కడ voltage ఎంత VDS ఉంది. So కాబట్టి not VDD. కాబట్టి the voltage drop across RG is can be written as VGS is equal to RG into VDS by RG plus RF. అంతేనా? Are you following or not? The voltage drop across the gate to source is ఎందుకు తీసుకుంటున్నాను ఇక్కడ ఉన్న రెండు ఈ ఇన్పుట్ కేవీఎల్ లో రెండే వోల్టేజ్ ఇక్కడ వోల్టేజ్ డ్రాప్ ఇక్కడ వోల్టేజ్ డ్రాప్ అంతే రెండే దిస్ కాల్డ్ ఇన్పుట్ అప్పుడు ఏమవుతుంది ఆటోమేటిక్ గా the voltage drop across this is equal to voltage of VGS కాబట్టి VGS is equal to రాసాం so voltage drop across RG ఏమవుతుంది this can be written as what is the voltage applied total voltage applied here is VDS not VDD be careful ఎర్లియర్ లో వోల్టేజ్ డివైడర్ బయాస్ తో మనం ఇంతకుముందు ఈ రెసిస్టెన్స్ ని ఇక్కడ కనెక్ట్ చేసాం కాబట్టి అప్పుడు VDD వేసుకున్నాం మనం ఇంకా అక్కడ కనెక్ట్ చేయలేదు VDD డ్రైన్ టర్మినల్ దగ్గర కనెక్ట్ చేసాం ఫీడ్బ్యాక్ మెథడ్ సో కాబట్టి వాట్ ఈస్ ద వోల్టేజ్ ఎగ్జిస్టింగ్ అట్ ది డ్రైన్ టర్మినల్ ఈజ్ VDS సో డ్రాప్ అక్రాస్ RG is RG into VDS by total resistance because these two resistance are in parallel combination RG plus RF. So VGS is equal to RG into VDS by RG plus RF. The rest of the things are same, right? Rest of the things are common. When you write the KVL on output side, you can write here, right? Output side KVL you can write here, right? And analysis you can go through as usual, right? Analysis part you can go through as usual. Sometimes we can also use a source resistance here. Sometimes a resistance of source is connected here. A source resistance is connected here. So that also we can do analysis part. The total applied voltage is equal to RG. Drop across RG is equal to VGS plus drop across RS. Is it fine? Entire losses circuit. Just draw. This is RS, this is the gate, this is VGS, the drop across this is VS, source voltage drop, and here the gate resistance RG, right? And the total resistance RG. A biasing of here. So, what is the drop across this? This drop across this voltage is just I am taking as VGG. Drop across this is VGG. Okay. Then VGG is equal to VGS plus ID into RS. So VGS is equal to VGS is equal to VGG minus ID into RS. See. Just like a previous condition what we have given in the previous step. So without source resistance you can write like this, with source resistance you can write you can write like this. So this is about the drain to gate gas. About the drain to gate gas. So these are the three types of biasings which I have covered, right? So first one is the fixed bias. In the fixed bias, we have gone through. Right, in the fixed bias, common source bias, without any source resistance, we have given this analysis part. Right, just VGS is equal to minus VGG. What is the voltage applied? Sometimes if the voltage is not given, just VGS is equal to 0, right? This is already minus 1K. And coming to the next method is fixed bias with RS. Fixed bias with RS. So here just I have to go through the circuit here on input KVL and output KVL. So we got VDS one equation and VDS another equation. VDS is equal to minus ID into RS. So drop across this is equal to VGS because there is no gate voltage. Gate drop here. If any gate drop is there, then VG minus VGG minus ID RS. Because 0 voltage is కాబట్టి మనం minus ID into RS రాస్తాం. Okay. And coming to the third one, voltage divided bias. This also emitter resistance is there, so it is called self bias, self voltage divided bias. So in that one, the total resistance are in parallel. So drop across R2 will acting as a input voltage, gate voltage to this gate junction. So that we have shown here, right? Analysis part. Right? This is the equivalent circuit we have drawn here. This is the equivalent DC equivalent circuit. After the voltage drop across this, I'm showing as a voltage source here, that is VGG. And this VGG voltage is applicable to the gate source junction. Right? The voltage across the gate source is VGS this nano. The voltage drop across RS is equal to ID into RS because the current flowing through entire the FET is ID only. There is no question of any IS. IS almost 0. Right? So ID is equal to IS. So based on that, I gone through this analysis part and I got the equation at VGS is equal to VGG minus ID into RS. And on outputs are KVL, I got the VDD is equal to ID into RS, RD plus RS plus VDS. So you can only VDS this one. VDS is equal to VDD minus ID into RD plus RS. RD plus RS. Right? So this is the expression what I got. And the last method is called as a drain to gate bias. ఇక్కడ రెండు రకాలు చూపించాము. I have shown two varieties here. One is without source resistance, with source resistance, right? And a gate voltage is applied here, right? Through by using the RG resistance, gate resistance is used, and the RF resistance is not connected at the VDD. It is connected at the drain terminal, right? So that apply the feedback of okay. What is the drain resistance? Drain current is generated here. The part of this drain current is fitted and it is given to me, right? So this becomes ID plus, actually you can write this as the current flowing through this is ID plus IG and loss much. So ikkada poye current vachesi ID aitundi, ikkada poye current vachesi IG. Ala kuda antaru. You can treat like that also. The current flowing through this is IG. But IG current is 0 because the gate is reverse bias current. మనకు ఆల్వేస్ రివర్స్ బాస్ అవుతుంది కాబట్టి ఇక్కడ సారీ దిస్ ఇస్ ఎన్హాన్స్మెంట్. సో ఇక్కడ there is a positive current of IG is there because gate is not reverse bias current. So positive current is going. Okay. So you take this IG plus ID plus IG అనుకోండి ఇక్కడ పోయే కరెంట్ అని తీసేయండి. Right, so the current flowing through is IG equal to current ID. So the total current flowing here is ID plus IG. Like that also you can write. Right. Okay, the analysis is the same what we did in the previous. The feedback method chesam kada BJT lo, the same method KVL KCL you can write. Okay. So these are the three different methods we have gone through. And next, we have to go through some problems on this. Everyone, please take the paper and pencil, paper and pen. I will dictate the 5 to 6 problems, and I will give you a time of 10 to 10 minutes time. You will try to answer the things, right? Later on, I'll go through the explanation of each and every problem. Clear? Respond. Please respond. Anyone?
Okay, sir.
I'll dictate the problem. Just note down. Calculate the operating point. Calculate the operating point of the self-biased JFET having the supply voltage of VDD equal to 20 volts. VDD equal to 20 volts. Maximum value of drain current. Maximum value of drain current IDSS equal to 10 milliamps. IDSS is 10 milliamps and VGS is equal to minus 3 volts at ID is equal to 4 milliamps. Also determine the value of resistors RD and RS to obtain this bias condition. To obtain this bias condition. That is the first problem. Clear? First problem. Calculate the operating point of the self-biased JFET having the supply voltage VDD equal to 20 volts, maximum value of drain current IDSS is equal to 10 milliamp and VGS equal to minus 3 volts at ID equal to 4 milliamp. Also determine the value of resistors RD, capital RD and capital RS to obtain this bias conditions. Right? Second problem. అందరూ రాసుకుంటున్నారా?
Yes, sir.
రాసుకుంటున్నారా లేదా కూర్చున్నారా? సార్ రాసుకుంటున్నా మన మీద రాసుకోవాలనుకుంటున్నారా? అనుకోదండి. I will see the notes while coming to the college. ఆన్లైన్ క్లాసెస్ కి నోట్సెస్ నేను అబ్జర్వ్ చేస్తూ ఉంటాను. వచ్చిన తర్వాత all notes I will verify. Right? Second problem. Calculate the values of RS source resistance required to self-bias an N-channel JFET. An N-channel JFET with IDSS equal to 40 milliamp, EP pinch off voltage EP equal to minus 10 volts and VGSQ is equal to minus 5 volts. Calculate the values of RS required to self-bias an N-channel JFET. ఒక N-channel JFET self bias చేయడానికి ఎంత RS వాల్యూ కావాలి? దానికి రిక్వైర్డ్ డేటా ఏంటి? Given that IDSS is equal to 40 milliamps ఇచ్చాడు, VP minus 10 volts and VGSQ is equal to minus 5 volts. Right? Calculate third problem. Calculate the Q point of this is repeated. What is that? A JFET amplifier with a voltage divided bias circuit has the following parameters. VP equal to minus 2 volts, IDSS equal to 4 milliamp, RD, capital RD equal to 910 ohms, RS equal to 3 kilo ohms, R1 is equal to 12 mega ohms, R2 equal to 8.57 mega ohms, and VDD equal to 24 ohms. Find the value of the drain current. The drain current ID at the operating point, at Q point. Okay. Find the voltage of the drain current ID at Q point. Right? These are the three problems. So take 10 minutes time and start doing. Starting from first problem. Take the calculators also with you, or keep the calculators with you, and try to solve these problems. I'll give for 10 minutes time, and you complete within 10 minutes. Right? I will stop the screen sharing, right? Because I have to do this. After completing the solutions, then I will explain. Okay, now? How many are hearing here? How many are hearing here? Only 63. One is absent. Please try to complete the problem. Please try to complete the problem. Simultaneously, I am also doing here. Okay, now, all of you, are you here? Are you there? Hello.
Yes, sir.
Yes, sir.
Complete.
Yes, sir.
Yeah, completed, huh? Are you completed? Hello.
Sir.
Yeah. So for the first problem, calculate the operating point of a self-biased JFET having the supply voltage of VDD 20 volts. VDD is 20 volts ఇచ్చారు. Maximum value of drain current IDSS, drain to source saturation current is 10 milliamp. And already awesome. So the drain to saturation current is this value. This is IDSS. The maximum approximately when VGS is equal to 0. VGS is equal to 0. As VGS goes on decreasing, -1, -2, -3, the IDSS value goes on decreases. So the maximum value for VGS is equal to 0, we are getting an IDSS. So that is called as drain to source saturation current. This is applicable only for JFET and DMOS. Yet this JFET is there. So probably and the maximum current IDSS and VGS of -3 volts applied. VGS of -3 volts applied and then drain current of 4 milliamp. Up to the drain current of -3 the point is equal to 4 milliamp. If ID is 4 milliamp. The IDSS is 10 milliamp. So determine the value of resistors RDN. So first one operating point. Operating point Q of VDSQ, IDSQ. The point operating point draw just Q draw. Q of what is the value of VDS? What is the value of IDS? VDS, IDS. This is called as VDS. X-axis VDS is present. Y-axis ID is present. So VDS రావాలి ఇక్కడ ID రావాలి. VDS and ID key point కాబట్టి I'm thinking as operating point should be always exact at the center of this pinch of region. The pinch of region లో మనం డ్రా చేస్తాం key point exact at center లో. కాబట్టి based on that sentence I'm making that IDQ is equal to IDSS by 2. Right? IDSS by 2. We are making that operating point Q is exactly at the center of the pinch of region. Based on that sentence or based on that statement, I am taking that Q point is exactly at the center. So, exactly at the center of the maximum value of IDSS is exactly half an hour. Now, the IDSS by 2. So, this becomes 5 million. Other than the VSQ, VD the maximum by 2. That is 10 minutes. Right? So, just I am writing this equation here because this is self-biased. So, what is the RD value and RS value I have to find out. So, for this one, just I am writing the equation on output KVL. VDS is equal to VDD minus, right, ID into RD. VDS is ID into RD. So, based on that, I get RD. If RS is there, then VGS is equal to minus ID into RS. This already derived equation. Fixed bias itself, fixed bias with source resistance RS. Fixed bias with source resistance RS. VGS is equal to minus ID into RS. Calculate this one. So our equation use case, I am just finding the RS. Clear? Clear? Any doubts? This is a textbook problem. You can just go through the textbook also if not understand properly. Right? And next problem is a very simple problem. Just using the FET current equation. I'm just using the FET current equation. Calculate the value of RS required to self-bias. Self-bias ఉన్నప్పుడు వెంబడి RS పెట్టేస్తాము. ఆటోమేటిక్ RS పెట్టేసారు. అది ఏ bias అయినా కావచ్చు. ఫిక్స్డ్ bias కావచ్చు, వోల్టేజ్ bias కావచ్చు. But you have to include source resistance RS. Right? So, calculate the value of RS required to self-bias and N-channel JFET with IDSS, drain to source saturation current of 40 milliamp and the pinch of voltage of -10. Pinch of voltage in the is a maximum voltage at which the pinch of process occurs. Right? Pinch of phenomenon occurs. Or the electric field is created, a narrow gap is created between the two barriers, gate barriers. Right? A fixed amount of current is flowing at pinch of region. Right? A fixed amount of current flows. So at what voltage this occurs, that is called as pinch of voltage. So the across -10 volts. And the -10 volts in the meaning this is called as a gate voltage. గేట్ వోల్టేజ్ VGS నేను -10 volts అప్లై చేసినప్పుడు ఆ పించ్ ఆఫ్ రీజియన్ వస్తుంది. VP -10 volts, రైట్? అప్పుడు ఆపరేటింగ్ పాయింట్ ఎక్కడ ఉంది ఎగ్జాక్ట్లీ అట్ ద సెంటర్. అది ఎప్పుడు అక్కడ ఉంటుంది సెంటర్లో. ట్రాన్స్ఫర్ క్యారెక్టరిస్టిక్స్ తీసుకున్నప్పుడు మీరు ట్రాన్స్ఫర్ క్యారెక్టరిస్టిక్స్ ఇలా తీసుకున్నప్పుడు ఇస్ మ్యాక్సిమం ఐడిఎస్ఎస్ మ్యాక్సిమం వస్తుంది ఎగ్జాక్ట్లీ అట్ ది సెంటర్. పించ్ ఆఫ్ ఎంత పించ్ ఆఫ్ రీజన్ ఎంత ఇక్కడ పించ్ ఆఫ్ రీజన్ బట్ ఎగ్జాక్ట్లీ సెంటర్. ఈ పాయింట్ తీసుకోవడం తీసుకోవాలి VGS నెగటివ్, రైట్? జేఫిట్ దగ్గర VGS జేఫిట్. కాబట్టి ట్రాన్స్ఫర్ క్యారెక్టరిస్టిక్స్ ఆల్వేస్ లైస్ ఇన్ ద సెకండ్ క్వాడ్రంట్. కాబట్టి ఎగ్జాక్ట్ అది సెంటర్ ఈ పాయింట్ అవుట్ తీసుకుంటాం. కాబట్టి VP 10 volts ఇచ్చినప్పుడు ఆటోమేటిక్ VGSQ ఎంత ఉంటుంది -5 volts ఉంటుంది, రైట్? సో based on that, I am just taking the ID current equation. ID is equal to IDSS into -1 VGS by VP whole square. దీని నుంచి I calculate the ID. Any values తెలిసినవి, right? VGS is equal to -5 volts, VP is equal to -10 volts, -5 volts by -10 volts, and this is whole square change. IDSS is given as 40 milliamps, right? Substitution. So it is comes under 10 milliamps. After getting 10 milliamps, then I have to find out VDSQ, right? VDSQ is equal to ID into RS. ID into RS. So done into RS conversions, right? And coming to the next problem, a JFET amplifier with a voltage divider bias. Already ఇచ్చేసారు voltage divider bias అని. దానికి ఫాలోయింగ్ పారామీటర్స్ ఏంటి? VP -2 volts ఇచ్చాడు, IDS -4 milliamps ఇచ్చాడు, RD ఇచ్చాడు, RS ఇచ్చాడు, R1 R2 ఇచ్చాడు, ఇవన్నీ. సో voltage divider bias అంటే మీరు వెంటనే you have to draw the voltage divider bias, right? Copy RS plus VB is R1 R2. ఇంకా దీనికి మనం చేసాం కదా ఆల్రెడీ. R1 R2 ఇచ్చాడు, మనకి దీంట్లో వోల్టేజ్ డ్రాప్ వచ్చేసి ఇక్కడ వోల్టేజ్ ఇన్పుట్ సర్క్యూట్లో అప్లై అవుతుంది. దాని ప్రకారం ఈ గో బ్యాక్ టు ద వోల్టేజ్ డివైడర్ బియాస్. దాంట్లో ఫార్ములాస్ రాశాను, రైట్? దాని ప్రకారంగా ఈ జస్ట్ గో టు. సో వోల్టేజ్ డ్రాప్ అక్కడ దిస్ ఈజ్ VGG అనుకుంటున్నాను. దట్ ఈస్ ఈక్వల్ టు VDD ఇంటూ, సో ద వోల్టేజ్ డ్రాప్ అక్రాస్ దిస్ ఈజ్ VGG. So VGG is equal to what is supply voltage into R2 by R1 plus R2. That becomes 10 volts వస్తుంది. సబ్స్టిట్యూట్ చేసుకోవాలి, రైట్? తర్వాత VGS కనుక్కోండి. VGS is equal to across this input circuit. VGS is equal to VGG minus ID into RS. రివైర్ కరెంట్ కూడా ID పెట్టాను. రివైర్ కరెంట్ కూడా ID. ఇక్కడ మాత్రం ID is equal to IS పెట్టుకున్నాం. FET మాత్రం మనకు BJTలో I is equal to IB plus IC వస్తుంది, కానీ అక్కడ IB స్మాల్ అమౌంట్ ఉంటుంది రీకాంబినేషన్ కరెంట్. ఇక్కడ రీకాంబినేషన్ కరెంట్ ఏమి ఉండదు, రైట్? టోటల్లీ IB is equal to IS అవుతుంది. కాబట్టి 10 VGG I got 10 volts, but 10 volts రాసాను మైనస్ ID into RS, రైట్? ID into RS ఎంత వచ్చాము? RS is given as 3 kilo ohms. So this is equal to 10 volts minus ID into 3 kilo, right? Now I am using this into the find the value of drain current ID at Q point, right? Q point there మనము values కనుక్కోవాలి, ID value కనుక్కోవాలి. So ID is equal to IDSS into 1 minus VGS by VP whole square. నేను ఇక్కడ ID and IDSS రెండు కరెంట్ మిల్లీ ఆంప్స్ ఉంది కదా, ఇక్కడ మిల్లీ ఉంది, ఇక్కడ మిల్లీ ఉంది. కాబట్టి మిల్లీ క్యాలిక్యులేట్ చేసేస్తాను, తీసేస్తాను, రైట్? తీసేసి రెస్ట్ ఆఫ్ థింగ్ ఐఎమ్ రైటింగ్, ఓకే? ఇక్కడ కూడా అంటే ఐడి వచ్చేసి మిల్లీ వస్తుంది, ఇక్కడ RS వచ్చేసి కిలో ఉంది. When I write milli and kilo, we will cancel out here. So simply I am writing the value 10 volts minus ID into 3. Are you following or not? అర్థమవుతున్నాయి కదా? ఐడి ఈజ్ ఈక్వల్ ఇక్కడ మిల్లీ వస్తుంది, ఐడి ఈజ్ ఈక్వల్ మిల్లీ ఆంప్స్ వస్తుంది, ఇక్కడ ఆర్ఎస్ వచ్చేసి 3 కిలో ఓమ్స్ ఉంది. కాబట్టి ఇక్కడ కిలో, ఇక్కడ మిల్లీ రెండు క్యాన్సిల్ అయిపోతుంది. కాబట్టి ఐడి ఇంటూ 3 వస్తుంది. ఇక్కడ కూడా ఐడి మిల్లీ యాంప్లో ఉంటుంది, ఐడిఎస్ఎస్ కూడా మిల్లీ యాంప్లో ఉంటుంది. ఐడి మిల్లీ యాంప్లో ఉంటుంది, ఐడిఎస్ఎస్ మిల్లీ యాంప్లో ఉంటుంది. సో ఈక్వల్ కాబట్టి ఇక్కడ మిల్లీ క్యాన్సిల్ చేస్తుంది. కాబట్టి జస్ట్ ఐడి ఈజ్ ఈక్వల్ 4 ఇంటూ ఆర్ వస్తుంది. యాక్చువల్ ఏముంది ఐడిఎస్ఎస్ 4 మిల్లీ యాంప్లు. కాబట్టి నాకు వచ్చే వాల్యూ ఐడి ఈజ్ ఈక్వల్ మిల్లీ యాంప్లు కాకుండా జస్ట్ ఈ వాల్యూస్ యాంప్స్ రిప్రజెంట్ చేస్తుంది. So it is equal to 4 into this one. So if you simplify this, you can get a quadratic equation of the quadratic equation of that is equal to 9 id square minus 73 id plus 144 is equal to 0. The quadratic equation of the quadratic equation solve just you can get id is equal to 2 values, 2 different values. Id is equal to ఒకటి వచ్చేసి 3.9 వస్తుంది, ఇంకో ఐడి వచ్చేసి 4.72. దిస్ ఇస్ టెక్స్ట్ బుక్ ప్రాబ్లం. 3.9, 3.39, 4.72 మిలియన్స్ వస్తాయి. ఇక్కడ 2 వాల్యూస్ వచ్చాయి కదా, విచ్ వన్ ఇస్ కరెక్ట్? యూ హ్యావ్ టు జడ్జ్మెంట్ హియర్. సో జనరల్లీ మనకి కండిషన్ ఏమి, ఐడి షుడ్ నాట్ ఎక్సీడ్ ద ఐడిఎస్ఎస్ బికాస్ ఇట్ ఇస్ జేఫిట్ కదా. జేఫిట్లో మనకు క్యారెక్టరిస్టిక్స్ ప్రకారము, మనకు ఉండే క్యారెక్టరిస్టిక్స్ ప్రకారము VGS is equal to 0 ఎక్కడైతే అవుతుందో అక్కడే మనకు మ్యాక్సిమం కరెంట్ వస్తుంది ఐడిఎస్ఎస్. రెస్ట్ ఆఫ్ ది VGS వాల్యూస్ -1, -2, -3 మనకు VGS ఎంత తీసుకున్నాం ఇక్కడ, VGS is equal to ఇది వస్తుంది 10 volt minus of this one. కాబట్టి మనకి ఇక్కడ వచ్చే వాల్యూ ఏదైనా సరే లెస్ దాన్ దిస్ వాల్యూనే. కాబట్టి ఐడి వాల్యూ ఎప్పటికీ దీనికంటే ఎక్కువ దాటకూడదు. కానీ ఐడిఎస్ఎస్ మనకి 4 మిల్లీ యాంప్ ఉంది. కాబట్టి మనకి రెండు వాల్యూస్ ఏది 4 మిల్లీ యాంప్ లెస్సర్గా ఉంది, 3.96, 3.39. 4.72 తీసుకుంటే ఇట్ ఈస్ మోర్ దాన్ ఐడిఎస్ఎస్. కాబట్టి ఈ వాల్యూ నాట్ వ్యాలిడ్, ఈ వాల్యూ నాట్ వ్యాలిడ్ తీసుకోవాలి. సో ఇది ఒక వాల్యూ తీసుకోవాలి. ఐడి ఈజ్ ఈక్వల్ టు 3.39 మిలియన్. సో దిస్ ఇస్ ద కరెక్ట్ ఆన్సర్, రైట్. సో లైక్ దిస్ యూ హ్యావ్ టు జడ్జ్ ద థింగ్స్, రైట్. సో yeah, so these are the different biasing techniques of field effect transistor, and some problems I solved. Tomorrow also we will go through 1 or 2 problems, and FET acts as a VDR. After that, then we will go for a remaining topics. Any doubts you can raise now. If you have any doubts you can raise, or otherwise you can ask tomorrow class also. Tomorrow also we will go through 1 or 2 problems, right? Then we will go through next topic. Hello students, how are you? Are you hear me? Just vinandi koncham. Hello, please respond.
Yes sir. Yes. Yes sir.
Yes, sir.
You are
Yes,
coming,
sir.
responding very late, I think. So you are doing some navigation, I think. You are busy with some other work? Huh?
No, sir.
Okay.
No, sir.
So
No, sir, no,
you can, okay, you can go through this again today, and tomorrow we'll go 1 or 2 problems because in the morning we have one first hour, say 9:30. After that, from Saturday we will start again in new topics. Most only 2 or 3 classes enough for completing this syllabus. 3 maximum 3 classes. Okay, now? Right. Thank you. I will stop now. I will end now here. Again, if you have any doubts, you can raise. Students. So if you not have any doubt, then I will stop. Thank you. Thank you.
Thank you.